So hello and welcome to another week of the NPTEL Algebra-II course, and I am one of the PMRFTs for this course. My name is Shubhajit Das. You can find my email ID on the screen, and this is week 11. As we keep doing every week, we'll be solving problems based on the content of the ongoing week, and I do hope that you are also attending Ajay Prajapati's sessions. He is another TA for this course. So let us begin. So let us have a look at the first problem. So we take an R module M where R is a commutative ring. We have to choose the correct answers. So option A says that M tensored over R with Rn is an RR bimodule. Now, since R is a commutative ring, you already know that every left R module is also a right R module, and conversely. So any R module is always an RR bimodule. So option A is clearly correct. There is no doubt about that, because M is an RR bimodule and R power n is again an RR bimodule. So their tensor product will be an RR bimodule, tensor product over R. Now option B says that M tensored over R with Rn is isomorphic to M power n. And since we have been talking about tensor products for quite some time now, so we know that tensor products distribute over direct sums, and using that we can conclude this. So option B will also be correct, and option C is clearly incorrect. So let us just write down the arguments. So option A is correct, as R is commutative, so that every R module is an RR bimodule. What about option B? Now M tensored over R with Rn is just isomorphic to, or is in fact equal to M tensored over R with the direct sum of n copies of R. And since tensor products distribute over direct sums, this is isomorphic to the direct sum of n copies of M tensored over R with R. And you know that any R module tensored over R with R gives you that R module. That is, R is sort of a unit object for this operation of tensoring over R. So this is just isomorphic to direct sum of n copies of M, which is just M power n. So option B is correct. So A is correct, B is correct, and option C is not correct. Correct, as otherwise, since option B is correct, M power n would be isomorphic to R power n for all R modules M, which is absurd, which is absolutely absurd. So option A is correct and option B will be correct. Nothing else will be correct. Okay. So let us move on to the next problem. So you take an abelian group A, which, as you already know by now, is the same as a Z module. Now you need to choose the correct answers. So option A says that A tensored over Z with Q is equal to 0. Now just looking at, so A is clearly incorrect. As taking A equal to Z gives Z tensored over, gives Z is isomorphic to Z tensored over Z with Q, right? and z is clearly not 0, right? So A is not correct. What about option B? Option B says that if every element of A has finite order, then the tensor product is 0. Now you know that the tensor product is generated by elementary tensors x tensored y, where x is in the first z module and y is in the second one. So if you can show that every elementary tensor is 0, you are done, right? So take any elementary tensor x tensored with let's say just y in A tensored z q. Since x in A has finite order, there exists some n in natural numbers such that n x is 0. Thus x tensored with y, which can also be written as x tensored with ny by n, which can therefore be written as, since n is a scalar, it's an integer, you can pass it to the other side. So this is nx tensored with y by n, which is 0 tensored, which is 0 tensored with y by n, which is just 0. Thus every elementary tensor is 0. Since the elementary tensors generate the tensor product, hence this is equal to 0. Thus option B is clearly correct. What about option C? So you are given that if the tensor product of an abelian group with Q is 0, then every element of it should have finite order. In other words, what this says is that if the tensor product with Q is 0, then A has to be a torsion abelian group, right? So how do you proceed to solve a problem like this? You know that every elementary tensor is 0. Now, yeah, so maybe I'll pause for a minute for you to think. So think about this carefully. You are given that the tensor product of A with Q is 0. Is it true that every element of A has to be finite order? If it is not, then you can come up with a counter example. Okay, so let us just quickly solve this. Suppose A tensored over Z with Q is given to be 0, but there exists A in A such that order of A is not finite. Then the submodule generated by A, the Z submodule of A generated by the element little a, is isomorphic to Z as I mean, yeah, I should, yeah, as I mean, it's clear. So as Z modules. Now I'm trying to avoid something here, so let me see if I can get around with this. Well, maybe not. So basically my point is that this, so you have a monomorphism of the submodule generated by A into A. That is a canonical inclusion. So this implies that this map will be canonically included in A tensor over Z Q. So what is this map? This, let's call this inclusion. So this is I tensored with 1Q. Now the reason this folds is precisely because Q is something called a flat Z module. So what is a flat Z module? A flat module is essentially a module over a ring A such that if you take tensor products with that module, then that should preserve monomorphisms or injections. So what I mean by this is, if n and n prime are two modules and you have an injective mapping of n into n prime, so first of all we start with a module M and a module M. Then we'll call M to be a flat A module if for any two A modules n and n prime, any injective A linear map from n into n prime, the corresponding map from n tensored over A with M into n prime tensored over A with M is injective. Okay, so maybe I'll write a better notation for this arrow. Okay, as Q is a flat Z module, hence tensoring with Q preserves monomorphisms or injections. Okay, and therefore from this what we get is thus Q, which is isomorphic to Z tensored over Z with Q, which is isomorphic to this tensored over Z with Q. Since A has been assumed to have infinite order, so the submodule generated by it will have to be isomorphic to Z, and this is a this is a submodule of A tensored over Z with Q, which is equal to 0. Contradiction. Hence C is not correct, because Q otherwise would be contained in 0, which is absolutely absurd. Hence C is not correct. So option A is incorrect, option B is correct, while option C is again incorrect. Okay, so let us move on to our next problem. So let R be a commutative ring, let M and K be R modules. Then which of the following are correct? So first of all, again as usual, option A is correct. A is correct, as M direction N, as R is commutative. So every left R module is every R module is an RR bimodule. So this is done. Option B says that, okay, so this is again your usual fact. So B is correct, as tensor products distribute over direct sums. Option C says that options, so indirect sum, yeah, so whether this would be correct or not, we can come up with an example in this situation. So what example can we have here? Okay, so yeah, we can just take so C is incorrect. Take M to be equal to R, the ring R, as considered as a module over itself. K to be equal to R again, and you take N to be equal to R square, R direct sum R. then M direction K tensored over R with N is isomorphic to R direction R tensored over R with I hope this is correct. Let me just, yeah, so tensored over R with R square, which is isomorphic to, oops, I forgot to write the tensor, which is isomorphic to R square tensored over R with R square, and you know that this is just R to the power 4, while it is on the other side. M direction N tensored over R with K direction M is isomorphic to R direction R square tensored over R with R direction R square, which is isomorphic to R cube tensored over R with R cube, which is isomorphic to R power 9. And we'll see, and R power 9 can never be isomorphic to R power 4. We'll see this later. I mean, I've included an exercise for this later. So R power 9 cannot be isomorphic to R power 4. So so let me just check the question number which I took. Yeah, so it's 8. So C, problem 8. Okay, and what about option D? So okay, so option A is correct, option B is correct, option C is incorrect, and D says that M tensored over R with K tensored over R with N is isomorphic to, yeah, so you know that tensor products are associative, so this is obviously correct. As tensoring over R is associative up to isomorphism, certainly. In fact, not only just an isomorphism, since you already know what natural transformations are, this is true up to natural isomorphism. So the left hand side, you can consider this to be a functor of 3 variables, M, K and M, and on the right hand side you again have a functor of 3 variables, and there is a canonical natural isomorphism from the first functor to the second functor. Oops. Yeah. So option D is again correct. Okay. So up to natural isomorphism, up to a natural isomorphism. Okay. So let us move on to our next problem. Question 4 says that you consider the ring Rx and consider the ideal generated by x square plus 1. You need to choose which of these options are correct. So before we get into the options, we quickly observe something, that ideal generated by x square plus 1, I mean the polynomial x square plus 1 in Rx is irreducible. And what else can we observe? Thus x square plus 1 being monic as well is the minimal polynomial or irreducible polynomial of I, the imaginary unit, over R. Hence C, which is isomorphic to R adjoined with I, is isomorphic to Rx mod ideal generated by x square plus 1, that is Rx mod I. Okay, so this much we know, that Rx mod I is isomorphic to C as rings, and hence R modules in particular. Now let's look at option A. Option A says that C tensored over R with Rx mod I, which we just saw is C, is isomorphic to C as R module. Now A is incorrect, as the left hand side is isomorphic to C tensored over R with C, which is just isomorphic to R square tensored over R with R2 as R modules, so which is isomorphic to R power 4, right? But RHS is isomorphic to C, which is isomorphic to R square. I mean, RHS is exactly equal to C, which is isomorphic to R square. And you know that R square and R power 4 cannot be isomorphic because they are R vector spaces, their dimensions are different, they can't be isomorphic. So option B is correct by the observation above. That C is isomorphic to Rx mod I as R modules. They are isomorphic as rings, and hence they are isomorphic as R modules in particular. And I mean, yeah, I should be very precise here. They are isomorphic as rings doesn't imply they are isomorphic as R modules. The fact that there is an isomorphism of rings from the first onto the second, or that is to the second, which fixes R. Such an isomorphism exists. So as they are isomorphic as R algebras, and hence they are isomorphic in particular as R modules. What about option C? Option C says that C tensored over R with this is isomorphic to Cx mod I. Okay. Now you recall this result. If M is an A module, then for any ideal, what kind of ideal? Then for any ideal, alpha containing A, M tensored over A with A mod alpha is isomorphic to M mod alpha M as A modules. Hence, using this result, and this is very easy to show because you already know that you have if alpha is an ideal of A, that is it's an A submodule of A, you have a right exact sequence of A modules, and tensoring with any A module preserves right exactness because it's a left adjoint. I am sure I have been talking about this a lot in the past few weeks. So it will preserve left adjoints, and from that you will get this result. Or you can directly use the universal property of the tensor product. So anyways, this result is correct. Hence, using this result, C tensored over R with Rx modulo I is isomorphic to C mod IC, right? It's isomorphic to C mod IC. Okay, no, I'm sorry, we can't use this result. C is not an Rx module, right? I mean, a priori it is not an Rx module. It can be made into one, but a priori it's not an Rx module, so it's not clear whether we can. I mean, we can't apply the result as such. But is there a better way to understand this? Let me think. Okay, so what would Cx mod I be? It's definitely not an integral domain, but can we say that? No. This is all about modules. We can't even be using results from integral domains or ring theory. So Cx mod I is an R vector space for sure. The right hand side is an R vector space of dimension 4 or of dimension 2 over C. The left hand side is two-dimensional vector space over C. What about this one? Cx mod I is again so Cx mod I will again be a two-dimensional vector space, right? So how can we see this? Let me think a bit. So this is clearly a two-dimensional vector space, right? Because yeah, it is. There is no doubt about that. But how to conclude? And the right-hand side is also a two-dimensional vector space. Over C. I mean, it's very apparent that they will be isomorphic, but I am unable to give a concrete answer to this. Okay, maybe we can do this by just a simple dimension counting. I guess that would be the right way to do this. So we don't need this result. So C tensored over, so C is correct. And why is that? C tensored over R with C, C tensored over R with Rx mod I, as we saw, is isomorphic to C tensored over R with C, which is isomorphic to C square as an R module. And on the other hand, Cx mod I On the other hand, Cx mod I is isomorphic to uh, what can we say about this? This is again, Cx mod I has dimension 2 over C, and this you can, by the way, this you can check easily by using the division algorithm, right? You can just take any polynomial fx, you divide it by x square plus 1. You are doing everything in Cx, so you get some polynomial of degree, I mean you get as a remainder you should get a polynomial of degree less than equal to 1, right? So that would suggest that Cx over I has dimension 2 over C, and hence I hope I am doing it correctly. Yeah, so it has dimension 2 over C, and hence is isomorphic to C2 as a C module, and hence as an R module. Because R is contained in C, two vector spaces which are isomorphic as C modules will also be isomorphic as R modules. Why? Because you take any isomorphism of one vector space into another, then that arrow will also be an isomorphism in the category of R modules. Right? So C is correct again. And what about option D? T is not correct. As LHS is finite dimensional over R, while RHS is not. So you know clearly that the polynomial ring over R will have infinite dimension over R. In fact, it has countable dimension, countably infinite dimension over R. So that is why D is not correct. So A is not correct. What about option B? B is correct. C is again correct, and D is incorrect. Okay. Okay, so let us move on to the next problem. So you know what M and C is, the ring of n cross n matrices over C. Now the first, you just need to figure out which of the two, that is M and C and Cx, which of the two is a C algebra. So clearly you know that the maps, that you know this, that the map, the morphism, yeah, clearly you know this, that the morphism, that is the map from C to Cx, given by including any complex number z, given by mapping any complex number z onto the corresponding constant polynomial, is a ring homomorphism. And since Cx is commutative, okay, so let me just write it in one line, and the image is contained in the center of Cx. Okay, so image is contained in Cx, which is equal to the center of Cx, because Cx is commutative. As Cx is commutative. On the other hand, the map, the arrow from So also the arrow from C to also the arrow from C to MNC sending every A onto A times the identity matrix is a ring homomorphism. And the image of this arrow is again contained in the center of MNC. You know that scalar matrices commute with every matrix, right? Thus both, so you get mappings of C into CX, so you get a mapping of C into CX and you get a mapping of C into MNC, and both these mappings makes CX and MNC into C algebras. Thus both are C algebras. That is option on, that is only option A is correct. Okay. Okay, so let us move on to the next problem. So you consider the ring R, you consider the ring end R. So you just look at R as a set. This is an object in the category of sets, and you can look at all arrows from R to R, right? That is, you can look at all endomorphisms in this category of the object R. The morphisms of R into R, that is a morphisms from R to R. And this is a ring under pointwise addition and composition, and you have a mapping phi which maps R into MR, this ring given as follows, that you map any real number R onto the function which sends every x onto Rx. Now you need to choose which of the following options are correct. So first one says that phi is a ring map. So A is correct, easy to see. You can just easily check this, since f of R plus S of x is equal to R plus S times x, which is equal to Rx plus Sx, which is equal to Fr of x plus, so I can just write it directly without making so many steps, Fr plus Fs of x. Now both Fr plus Fs and Fr plus S are mappings of R into R, and you know two mappings are equal if and only if they behave in the same way on the domain, right? They behave they are equal point wise or element wise. So this is true for all x in X, for all x in R, which implies f of R plus S is equal to f of R plus f of S for all R and S in R, right? And f Rs of x is Rs times x, which is equal to yeah, I should be clear, not point. So the operation on end of R is not operations are not pointwise addition and pointwise multiplication. I should be precise. The addition operation is pointwise, but the multiplication operation is given by composition. Yeah. So this can be written as Fr of Sx, which is Fr of Fs of x for all x in R, which implies that Frs is equal to Fr composed with Fs for all Rs in R, and that shows precisely that this is a ring homomorphism. You can also check that one goes to the identity now. Also, F1 is equal to the identity arrow from R to R. Right. So phi is a ring map, correct. Second one says that the image of phi is contained in the center of MR. That is, whatever is the image of phi, it should commute with everything in MR, right? So maybe I'll give you maybe 30 seconds to think about this, whether this should be correct or not. When you need to figure out whether image of phi is contained in the center of MR. So note that the image of phi consists of all maps FR, right? Whether they commute under composition with all elements of MR is something that you need to work out or figure out. So what do you think, whether this will be correct or not? So B is incorrect. And hence, since B is incorrect, C will also be incorrect, because you observe this, that they are saying that the action of R on MR, of the ring R on the ring MR, given by R dot F is defined with phi R composed with F, makes MR into an R algebra. Okay, so first of all, MR is a ring that you know, R is your base ring, so it's an R algebra if and only if the following two conditions will hold, right? First of all, MR is an R module, and moreover that module structure should be compatible with the ring structure on MR, and the compatibility is basically given by this condition that the image of the map phi, the map which gives you this algebra structure on MR, the image of this map should be contained in the center of MR. So if B is incorrect, automatically C will be incorrect, and hence C is incorrect. So it will check why B is incorrect. Okay, so take the map. This is, just recall, ender is just the set of all functions from R to R, that is mappings of R into R. So just take the arrow in the category of sets, take the arrow from R. Okay, we need a symbol for this, so take the arrow S mapping R into R. You take the arrow from R into R, sending X onto X bar. This is a perfectly well defined set map, and now if f of 2 composed with S of, let's say, maybe 1 is equal to f of 2 of 1, because 1 square is 1, so this is just 2, while S composed with f2 of 1 is S of f2 of 1, which is 2, which is equal to 4. Thus how do I write this in one line? Thus f of 2 belongs to im phi. I hope, yeah, it's phi, but f of 2 is not in the center of MR, because it clearly doesn't commute with the element S in MR. So B is incorrect, and therefore C is also incorrect. Okay, so let us move on to our next problem. So you need to determine whether this statement is true or false. Assume that V is a finite dimensional vector space over a field F. and you take v prime to be non-zero elements of V, then V tensored with V prime, and you assume that the elementary tensor V tensored with V prime is equal to the elementary tensor V prime tensored with V. So this is a true or false statement. You take a finite dimensional vector space V or a field F. You take two non-zero elements V and V prime of V. Then V tensored with V prime is equal to V prime tensored with V if and only V and V prime are linearly dependent over F. Whether this is true or false. So we claim that this is true. So certainly this arrow holds. I mean, this arrow exists, right? The opposite implication, this implication, that is linear dependence implies that the two are equal, holds clearly as V equal to AV prime for some A in F implies V tensored with V prime is equal to AV prime tensored with V prime, which is equal to, since A is in F and you are taking the tensor product over F, so you can move it to the other side. So V prime tensored with AV prime, which is equal to V prime tensored with V. So this one, the backward implication holds. Now what about the forward one? So let x1 up to xn be a basis of V over F. Let V is equal to summation AI xi and V prime equal to summation Vi xi. Maybe we'll use different scalars, I mean different indices, but all of both I and j run from 1 to n, of course, because we have assumed that x1 up to xn is a basis for the finite dimensional vector space V over F. Thus V tensored with V prime is equal to some AI xi tensored with some Bj xj, which is equal to some ij, sum over ij, ai bj times xi tensored with xj, right? While V prime tensored with V is equal to some bj xj tensored with some ai xi, which you can again write to be equal to sum. So yeah, so I mean some gi ai bj xj tensored with xi. Now by switching places for I and j, this you can write as some ij aj bi xi tensored with xj, right? Now since x1 up to xn is a basis for V over F and x1, I mean xi tensored with xj, this set is it generates the tensor product by the construction of the tensor product. V tensored over F with V which is isomorphic to Fn tensored over F with Fn, which is isomorphic to Fn square, and this set generates the tensor product, implies the tensor product is again an F module, that is an F vector space. So this implies that xi tensored with xj ij is a basis for V tensored over F with V over F. And finally what we have is this, that V, now V tensored with V prime V tensored with V prime. Okay, now summation AI Pj xi tensored with xj is equal to V tensored with V prime. So this is over ij, which is equal to V prime tensored with V, which which is equal to summation ij ajbi xi tensored with xj. Okay, so yeah, hi. You you joined a bit late as usual, but okay. So what I was doing is I was solving this problem. So I'll just give you a recap of this. So you take a vector space, finite dimensional vector space V over a field F, and you take non-zero elements of V and V prime. Then V tensored with V prime is equal to V prime tensored with V. This is these are just the elementary tensors in the tensor product of V with V over F. So these two elementary tensors will be equal if and only V and V prime are linearly dependent. That is what we need to show. Now one implication holds clearly, right? If V and V prime are linearly dependent over F, then V tensored with V prime can be written as A V prime tensored with V prime. And since A is in F, the tensor product is taken over F, you can switch A to the other side. So this is V prime tensored with A V prime, which is V prime tensored with V. So one implication is clear, obviously. Now let me ask you, the other way around is also correct. So the argument goes roughly like this, that you take x1 up to xn to be a basis of V over F, and you take V to be some ai xi, V prime to be some bj xj, and you can write V tensored with V prime as this, right? Summation, I mean, you can just compute, you can use the properties of the elementary tensors, that is, it splits over addition in each component, and you can switch scalars around to arrive at this expression. So this is your expression for V tensored V prime, and similarly if you keep on doing this for V prime tensored V, you arrive at this expression. Okay, so what we have right now is, I'll just write down the two expressions, sum ij ai bj xi tensored with xj. So the sum runs over I and j from 1 to n, and this is equal to the sum ij aj bi xi tensored with xj. These are just routine computations. So once this side is V tensored with V prime and this side is V prime tensored with V. Now computation here is not important. What I am asking here is, if these two elements of the tensor product are equal, can you conclude from this that ai bj will be equal to aj bi for all I and j? Did you understand the question? Yeah, so the xi's have been taken to be a basis of V over F, and now in V tensored over F with V, you have two expressions in terms of xi tensored xj. So on one hand you have, I mean, these things are the same, xi tensored xj, these are the same on both sides, but you have different scalars. So why can you conclude from this, if these two sums are equal, why can you conclude from this that the components, individual components, will also be equal? Okay, very good. And why is that? Yeah, but yes, so it will be a basis where, because it has to be linearly independent and it generates. But my question is, why is it linearly independent? For that, so what I'm trying to stress here is, do you actually need to write down an equation for linear dependence and show that the scalars are 0, that would take some time, right? I mean, it would take a lot of time, because that is some tedious kind of computation or calculation. But can you directly conclude or directly say that this xi tensored with xj, this will be a basis for V over F?
Because each residence which is on itself can be a basis for you.
Yeah, but how do you conclude from that that this will be a basis? Think about this for maybe a minute. Okay, so forget basis and all that. Just tell me what is the first thing that you can conclude about xi tensored with xj? Okay, so maybe I'll erase this. Let us just keep xi tensor with xj. Think of a more general situation. Assume M and N are modules over a ring A, or a commutative ring A, and assume that M has a set of generators xi, just generating set, and this has a set of generators yj. Okay, so can you say that what can you say about this tensor product? Is it true that, can you find a set of generators for the tensor product? Just by construction of tensor products, you already know this, right? That this xi tensored with yj, this will generate the tensor product, right? Because every element of the tensor product is a sum of this. Yes. So this will be a set of generators for the tensor product. Now come back to our vector space situation. You know that xi's generate V, and therefore this should be a generating set for V tensored over, sorry, where did I did it get erased? Here it is. So you know that xi's generate V as a vector space, or as a module over F. So this will be a generating set for V tensored over F with V, right? That much we can say. It will be a generating set. So the only thing to conclude that this set will be linearly independent, would be the only thing to conclude that this set will be a basis of this tensor product is to show that this set is linearly independent, right? Okay, tell me, V is a vector space over F, right? And hence it's an F module. Similarly, V is again an F module. You take the tensor product, this is an F module, and since F is a field, this is therefore a vector space over F. Can you say what is its dimension directly? Okay, and why is that? Without getting to this, that this will be a basis, this has n square many elements, because that would be a cyclic argument. Why is the dimension of this tensor product n square? So you know that V is isomorphic to Fn, right? The direct sum of n copies of F. And we already saw this many times previously, that tensor products distribute over direct sums. Namely, because taking tensor product with something is a left adjoint. So it should preserve direct sums in particular. And that would mean that this is isomorphic. So this is direct sum of n copies of F tensored with direct sum of n copies of F. And this would therefore be isomorphic to direct sum of n square copies of F, right? Also using the fact that any vector space tensored over F with F is isomorphic to the vector space. So using all these facts, we can directly conclude that this is just Fn square. So it has dimension n square over F, and therefore So this tensor product, whatever it is, it has dimension n square over f, and you have already found a generating set of n square elements, right? Which would mean that they have to form a basis, because if they didn't form a basis, that means they would be linearly independent, which would mean that you can take a subset of it, right? You can delete elements and form a basis, but that would again contradict the fact that it has dimension n square. So linear independence follows follows freely. Okay. So yeah, so that is what the argument is about, and hence ultimately what we have is these two expressions are equal, imply that ai bj is equal to aj bi for all I and j, which implies that ai over bi is equal to aj over bj for all I and j. You can just take this to be, take the common ratio. I don't even know if this is a very precise word, I mean now, I mean ratio thing, but yeah, take the common ratio to be lambda in f, and then it's very easy to see that v prime, which one is correct? Yeah, v is lambda times v prime probably, right? Because yes, yeah, and so we are done. So did you understand the argument? Okay, so let us move on to next problem. So this, oops, why did I not leave space? Yeah, so this is one of my favorite things about commutative rings, and that is why I wanted to include this. This was not in the assignment, but yeah. So you take a commutative ring R, then is it true that R power m, I mean direct sum of R copies of m, is isomorphic to R power n if and only if m is equal to n? Okay, so I should be very clear. As R modules. Sorry, as R modules. Okay, so R is a commutative ring. You take direct sum of n copies of R, and you take direct sum of n copies of R. Now the claim is that they are isomorphic if and only if m is equal to n. So what do you think? By the way, just a small thing to note here, if R is any ring, what is R power n actually? I mean, it's an R module that you know, but what is it actually? I mean, what kind of module is it? This is something called a, I mean, can you understand that this is an R module, right? And it has a basis, right? Namely this element. Exactly, the canonical basis. So even though it's not a vector space, you can still make sense of basis here. So these elements form a basis for R power n over R, right? So what is a module called when it admits a basis? What kind of modules, I mean, what are those modules called which have a basis? Exactly. So R power n is a free module. It's a finitely generated free module because it has a finite basis. In fact, any free module, you take any free module m over R, then that will be isomorphic to some R power some I, right? For some set I. May be infinite, may be finite. But you can show this easily using the fact that it has a basis. So the point of having a basis is that you can write the module as a direct sum of copies of the ring. Why direct sum? Because the direct sums have this interesting property, right? That suppose you take A direct sum B, then the point is that the elements of A do not interact with the elements of B, right? In a sense, they work independently. That is what direct sums are all about. And in the case of a basis as well, if you have vectors, the vectors are independent from each other, right? That is why you get this direct sum decomposition. That's just a very rough argument, not very precise, but yeah. So let's see this problem. You are given a commutative ring R you need to figure out whether r power m is isomorphic to r power n as r modules if and only if m is equal to n. So first of all, let us get back to the simplest case. So what happens if R is a field F? Then if these are isomorphic as vector spaces, does that imply that m is equal to n? That will be obviously true. You have already seen that any two bases for a vector space over a field F have the same cardinality. So certainly this is true if R is a field F. But what about a general commutative ring? What do you think? Okay, let me ask you this. You are given a ring, and so my claim is that this will be true. This is correct, and we want to use here the usual property that we know for vector spaces. That is, any two bases of a vector space have the same coordinate. That is what we want to get to, which means that we are just given a ring. We need to get out of it a field, right? So how do you make a ring into a field? How do you get a field out of a ring? Exactly. So that means if you are given a ring and if you can find a maximal ideal in that ring, you can obtain a corresponding field. There will be a canonical surjection of, there will be a canonical map of R of the ring onto the field, right? The projection map. Now my question is, if R is any general commutative ring, is it always true that it has a maximal ideal? No. Okay, why? Can you give an example? Did you not study Zorn's lemma in set theory? Yeah, and Zorn's lemma says this, right, that it will have a maximal ideal. Zorn's lemma is, even though we call it a lemma, but it's not actually a lemma, right? Exactly, because it's equivalent to the axiom of choice. So I was interested in set theory at some point, and so Zorn's lemma is, even though it was actually given by someone called Zermelo. So this ZFC, you have no ZFC axioms in set theory. Z is for Zermelo, F is for Frenkel, and C is for the choice axiom of choice. So Zorn's lemma was actually given by Zermelo initially, but it was proved by Max Zorn. That is why we call it Zorn's lemma, even though we shouldn't. Yeah. So so from Zorn's lemma, so just take a maximal ideal. M of R exists by Zorn's lemma. That much we can agree. Why? Because you just take the collection of all proper ideals. You show that this is inductively ordered. That is, collection of all proper ideals. This is a partially ordered set. Show that this poset is inductively ordered. That is, every chain in this has an upper bound. And then Zorn's lemma says that you get a maximal element, which will precisely be a maximal ideal of the ring. So take a maximal ideal M of R. So as you suggested, consider K is equal to R mod M. This is a field. Okay. Now tell me, what can we do next? So okay, so yeah, I'm rushing into things a bit. So we need to prove this is true if and only if, this is true if and only if this is true, right? So we already know that if this is true, then this is obviously true. M equal to N implies that they are isomorphic. We need to prove the other direction. So we just assume that this is true. So you are given this data that R power M is isomorphic to R power N as R modules. Now you have obtained a field out of the ring R. Can you change the R modules as well? If you can change the base ring, can you change the corresponding R modules? You know a trick, right? So you have this map. Yes, you have the canonical map R into R mod M. So you have this canonical arrow from R to R mod M in the category of rings. And my point is that this arrow is a ring homomorphism. Now you are given R modules, R power M and R power M. That is, you are given modules over this ring. Can you get modules over this ring out of this? What is that trick called? You are changing the scalars, right? From R you are going to R mod M. What is that trick called? It's called extension of scalars, right? Exactly. So by extension of scalars, consider R power M tensored over. So what is extension of scalars along this spring map? So if you take a map A to B, what is the extension of scalars? You take a module M over A and you send it to, this is a very bad notation here, but send in, I am writing it in a different place. So take M, a module over A, and you should send it to, and what is that module? What is the extension of scalars precisely? M is an A module. How do you get a B module out of M? You just send it to M tensored over A with B, right? You know that B is a B module, and hence by restricting the scalars, you see that B is an A module. M was already an A module, so this is an A module for sure, and moreover it has a B module structure. Why? Because you take any element here which is of the form sum mi tensored bi, you multiply it with B prime, and you define this scalar multiplication to be sum mi bi b prime, right? This is an element of the tensor product, which makes the tensor product into a B module. That is why we say that this is an extension of scalars. And what important thing do you know about extension of scalars? Okay, we'll get to this, but let us just write the extensions. So this is with R mod M, and you are also making R mod N into an R mod mid. I mean, you are also extending scalars for R mod M. So far what you know is this, both this and this are not only just R modules, but what kind of modules? These are, you have extended the scalars. So what kind of modules are this? Yes, R mod M modules. I am using too much space. Now tell me, so these are R mod M modules. Now tell me, can we say that this and this are isomorphic? We initially know that R power M and R power N are isomorphic. Can we conclude that the corresponding extension of scalars will be isomorphic? Why? Why is that the case? Because if you take any, that I understand, but that holds for R, as R modules. But why are the corresponding tensor products isomorphic as well? I mean, certainly if two modules M and N are equal, then taking tensor product over some thing with some common module will also be equal. That there's no doubt about that. But if they are isomorphic, why will be the corresponding tensor products isomorphic as well? This happens because so you take a ring map from A to B, the corresponding extension of scalars for any module M can be written as M tensored over A with B. Now take M as your variable. What is this exactly? This is your extension of scalars that sends m to m tensored over a with b. This is a map that I understand, but is it something more than just a map? It is a, so it takes elements from the category A, objects from the category A and arrows from the category A, and maps them onto objects and arrows respectively in the category MB, right? So what is a map of categories called? Sorry, I didn't understand. What is a map of categories called? A mapping of one category into another category. What is it called? What kind of maps do you study? Those are called functors, right? Yeah, so the right kind of maps that you study in case of categories are functors. And you again know that between functors you talk about natural transformations from one functor to another functor. So for categories, so a map of categories is called a functor, right? It's a mapping that maps one category into another category and preserves every ambient structure in the category, that is domain, codomain, composition, identities, etc. It maps objects to objects, arrows to arrows. So this extension of scalars is a functor, right? And you know this, of course, that functors preserve isomorphisms, right? Isn't it? Because if C and D are categories and you take, if C and D are categories and you take a functor F from C into D, assume F is an isomorphism in C, which means that it has an inverse G, so that F composed with G is equal to 1 on something and G composed F is equal to 1 on something. If you apply F will split on composition because it preserves the composition. It's a functor, so this will be 1 on something and similarly the other way around. So my point is that if F is an isomorphism, then its image under the functor will also be an isomorphism, and therefore from this you can directly say that since R power n and R power m are isomorphic as R modules, these two have to be isomorphic. Of course, you can just take an isomorphism from this to this, apply the extension of scalars functor. So this is an arrow in the category of R modules. If you apply extension of scalars, you get an arrow in the category of R mod m modules. So certainly, and this was an isomorphism, implies that the image arrow will also be an isomorphism. The point is therefore that they are isomorphic as R mod m modules. Okay. Now tell me, now you finish the argument for me. So these are both isomorphic as R mod m modules, and R mod m is a field, that means these are vector spaces over R mod m. Now can you say what is this isomorphic to? I mean, what is the dimension of this vector space, can you say? Think about this. So suppose if we just had, instead of R power n, if we just had R tensored over R with R mod m, what is this isomorphic to? Is it clear or am I getting you confused?
Is it isomorphic to R because R is commutative?
No, this is isomorphic to R mod m, right? Because if m is any R module, if you take tensor product with R, you just get back m, right? R sort of behaves as a unit object, right? The precise isomorphism sends m comma little r onto, sorry, m tensored with little r onto mr. This is an isomorphism, right? Yeah, so this will be isomorphic to R mod m. So if you had a single R, this is isomorphic to R mod m. Now you have n copies of R, that is you have direct sum of n copies of R, and you are taking tensor product with R mod m. You know that tensor products distribute over, yeah, you know that tensor products distribute over direct sums. So that would mean that this is isomorphic to direct sum of R tensored over R with R mod m, n copies, and as is always the case, this is just direct sum of n copies of R mod m. That is, this is isomorphic to R mod m power n, right? isn't it? And similarly, by the same argument, this is isomorphic to R mod m power m, right? So the left hand side and the right hand side are isomorphic. The left hand side is an m dimensional vector space, the right hand side is an n dimensional vector space. Using our results from vector spaces, yes, m is equal to m. So these are isomorphic as R mod m vector spaces, which implies that m is equal to n. So this is certainly correct. And the important thing that we needed here was the fact that R is a commutative ring, right? We did all these procedures and all that. There we needed that R is a commutative ring. Okay, because so why exactly did we, I mean, where exactly did we use the fact that it's a commutative ring? Namely, the fact that once you extend the scalars along R mod m, of course you can extend scalars for non-commutative rings as well, but once you extend scalars over R mod m becomes a field. I mean, R mod m is a field, right? That is where we are using the result, right? That is we are getting vector spaces over the field. Otherwise, R mod m could just be a division ring or something, and then you wouldn't be able to conclude further. So R is commutative is what is really important here. So this is a homework exercise for you. Find counter example. Of course, not in the commutative case. We have already proven the commutative case. Find counter example for non-commutative rings. Just a minute. Orgon, আমি পড়াচ্ছি, তুই যা, আমি পরে খেতে যাবো। Yeah, so find counter examples for non-commutative rings. So what I'm trying to say here is, so what we achieved is really important. We see that if R is a commutative ring, then any two free modules over R, I mean so what I'm saying is, assume R is a commutative ring, then any two bases of a free module over R will have the same number of elements. Just as we have the situation for fields, we have the same thing here. So if M is a free module over R, assume finitely generated, then M will be, and assume that it has a basis with n elements, then M is isomorphic to R power n as an R module. And also assume M has a basis with m elements, that would mean this is isomorphic to R power m as R modules. And we just saw that R power m and R power n are isomorphic, implies M is equal to n. So what this means is that any two bases of a free module over R have the same cardinality. So this is true for commutative rings, but this is not true for non-commutative rings. This is what I am asking you to find out. This, by the way, is also known as the invariant basis number property. Okay, so a ring is said to have this IBN property if any two bases of a free module over that ring have the same cardinality. And as we just saw that commutative rings do have IBN, but in general it's not true. So do find counter example for non-commutative rings. Okay, so we are only left with two problems. We'll just quickly end them. Yeah, if you have any questions you can ask me. Otherwise we'll continue. Okay, so which of the following Z modules satisfy ACC? So you know what ACC is, right? Ascending chain condition. So we are asking for Z modules satisfying ACC, means that we are asking for ACC on submodules, ascending chain condition on submodules. So tell me something, is Z, does Z satisfy ACC as a Z module? What are those modules called, by the way, which satisfy ACC? What is an R module called if it satisfies ascending chain condition on submodules? What is it called? It's called a Noetherian module, right? I hope you know this, or maybe it wasn't introduced in the course. Okay, so just as you have Noetherian rings, you can talk about Noetherian modules. In fact, this is much more general. You define a module to be Noetherian if it satisfies ascending chain condition on its submodules, which is equivalent to saying that every submodule is finitely generated, which is again equivalent to saying that every non-empty subset, non-empty collection of submodules has a maximal element. And there are many other equivalent ways to describe this, but what I'm trying to say here is this Noetherian modules are a generalization of Noetherian rings, because if you observe carefully, what is a Noetherian ring? It is a ring which satisfies ACC on ideals, right? Now, ideals of a ring are precisely the same as submodules of module are considered as a module over itself, right? So, R is a Noetherian ring if and only if it satisfies, if and only if it is a Noetherian module over itself. That is what I am trying to ask. Even though this Noetherian condition might seem a bit clumsy, or it's you might think that it's just a finiteness condition, what's the big deal, but it's really it has far reaching consequences in category theory, categorical algebra, and I mean it's a whole different story. So it's very surprising how Amy Noether came up with this notion, and she had so much insight into this. I mean, that's the definition of a Noetherian module is so simple, but it's absolutely brilliant. Anyways, we are digressing too much. Uh, yeah, so we need to find out which of the following Z modules satisfy ACC. So tell me, is Z does Z satisfy ACC as a Z module? Okay, why is that? Or equivalent way to say this is whether Z is a Noetherian ring or not. Z as a Z Noetherian as a Z module is the same as saying that Z is a Noetherian ring. Now, why is Z Noetherian? Why is this the case? Because you know that it's a principal ideal domain, and every PID is Noetherian, right? So A is correct, as Z is a PID, which means that every ideal is generated by a single element, which means in particular that every ideal is finitely generated, which means that every it's a Noetherian ring, and hence Z is Noetherian as a ring or a module over itself. Okay, so certainly option oops. So certainly option A is correct. What about option B? Is Z12 Noetherian or not? I mean, does it satisfy ACC on its submodules? ACC says that if you take there can be no infinite strictly ascending chain of submodules, right? Every ascending sequence of submodules will be stationary at some point. Exactly, very good. So Z12 is, so B is correct. I have to write so much. B is correct as Z12 is finite as a Z module. I mean the underlying set is finite. Yeah. So what about Q mod Z? Does it satisfy ACC? Does Q mod Z satisfy ACC? Okay, tell me, Q mod Z is a Noetherian Z module. Does it imply in particular that Q mod Z is finitely generated as a Z module? Because one of this is true, right? Because one of the equivalent conditions was that a module is Noetherian if and only if every submodule is finitely generated, right? Now Q mod Z is Noetherian would imply that every submodule of Q mod Z will have to be finitely generated. Now is Q mod Z, so in particular Q mod Z will be finitely generated as a Z module. Is it correct? Is Q mod Z finitely generated as a Z module? So uh, C is not correct. C will not be correct. Let me just write out the form, the first part of the argument. Q mod Z is, okay, how should I write this? Every Noetherian module is in particular finitely generated. As a module over the base ring, of course, but Q mod Z is not a finitely generated Z module. Why is Q mod Z not a finitely generated Z module? Chatra? Okay, tell me, is Q finitely generated as a Z module? Can you use the same argument to conclude that Q mod Z won't be finitely generated as a Z module? Why? Because you can just take any finite set of generators, right? Z plus a1 by b1 dot dot up to z plus an by bn in Q mod Z. These are elements in Q mod Z. Assume that they generate Q mod Z. Now take b1 up to bn, take all these integers. Of course, you can get a prime number which is not present in any of them, right? Because there are infinitely many primes. So just take a prime p which is not a factor of any of these integers, that is, which is not a factor of this product. Then clearly z plus 1 over p will not belong to the submodule generated by this, right? Is it okay? That much you can, I mean, that much you need to compute and see. But yeah, the argument is exactly the same as in the case of Q. Because there are infinitely many primes. So Q mod Z is not a finally generated Z module. If it would imply in particular that Q mod Z is not Noetherian. So C is incorrect. And what about D? Is this this is a polynomial ring in n variables? You can consider it as a Z module. Is this Noetherian as a Z module? Is this Noetherian as a Z module? Okay, forget so many variables, just concentrate on one. Is Zx Noetherian as a Z module? Again, use the same argument. If it were Noetherian as a Z module, then in particular it would be finitely generated as a Z module, right? Now is Zx finitely generated as a Z module? Why? Why is that the case? Because you again take a finite set of generators, let's say f1x up to fnx. These are just polynomials, right? They have a degree. Take the maximum of all their degrees and take some x to the power some larger power of x which is greater than the maximum of all their degrees. Then x power m cannot belong to this submodule generated by this, right? Because the scalars that you have here are only coming from z, and you are taking the submodule generated by this, which means that the only way to multiply something is to have a scalar and an element of the module. So any element of this submodule will be r1 f1 x plus dot dot plus rn fn x, right? Where ri's are integers and f1x are these polynomials. So you never get a polynomial of a larger degree, right? So that would mean that this is not finitely generated, which would in particular imply that this is not Noetherian. And the same argument will of course hold for this invariable ring. So D is not correct, as zx1 up to xn is not a finitely generated Z module. Even though it is very interesting to note here that even though this is not a Noetherian Z module, it is a Noetherian Z x1 up to xn module. I mean, this is also a ring in its own right, and you can consider the corresponding module over itself, right? You can consider this to be a module over itself. That will be Noetherian. That is what I am trying to say is, even though this is not Noetherian as a Z module, this is a Noetherian ring. Are you aware of Hilbert's basis theorem? Okay, so you know what Hilbert's basis theorem is, right? It says that if R is a Noetherian ring, then the polynomial ring Rx is also Noetherian. So Z was Noetherian, hence Zx1 will be Noetherian, and this is a Noetherian ring implies the corresponding polynomial ring, this is Noetherian, and this is just Zx1 x2. You can continue this for n variables. So this polynomial ring in n variables is Noetherian as a ring, but not Noetherian as a Z module. It's Noetherian as a module over itself, but not Noetherian as a module over Z. Okay, so A, B, C, D are so A and B are correct, C and D are not correct. Okay, and the final question is of course the dual version of this. We need to find out which of the above modules satisfy DCC. So tell me quickly, does Z satisfy DCC? Descending chain condition. Yeah, but does it? Does Z satisfy DCC? Why? Can you give me an example of a strictly decreasing sequence of ideals? Sorry? Okay. Okay. So yeah, so Z is, by the way, what are those modules called which satisfy DCC on their submodules? So that one was, previous one was called Noetherian, ACC, and DCC ones are called Artinian by Emil Artin. Okay, so how should I write this? Z doesn't satisfy DCC as a Z module, of course. Oops, we are almost done. Yeah, as a Z module, as 2Z contains 4Z, as you said. This is a proper containment which contains 6Z, which contains 8Z. This is a strictly decreasing sequence of ideals in Z, right? As you said, this is in Z. Okay, so Z doesn't satisfy DCC. Does Z12 satisfy DCC? Why? Exactly. So Z12 satisfies DCC as a Z module as it is finite. Okay, does Q mod Z satisfy DCC? Does Q mod Z satisfy DCC? Why? Why does it satisfy DCC? Why does Q mod Z satisfy DCC? Okay, so I'll leave this to you. I don't have much charge left, but yeah, this for this you need some argument. I mean, yeah, I am not confirming that this satisfies DCC or doesn't satisfy DCC or anything, but try to think about this. And what about the last one? Can you tell me quickly whether this satisfies DCC or not? Does it satisfy DCC? Can you cook up a strictly decreasing chain of ideals in this? Just focus on one value. Yeah, you're saying something. This doesn't satisfy DCC as a Z module. Yeah, I said ideals, I should be precise. Submodules. Can you find a strictly descending chain of submodules in this polynomial algebra? Maybe I'll call it an algebra. Yeah. So can you find a strictly descending chain of submodules here? Since you can just take the submodule generated by x1. This will contain the submodule generated by
Square.
sorry.
X1 square.
Yeah, this will contain this, and this will further contain x1 cube. Yeah, it's strictly decreasing and goes on, right? So you have found out a strictly descending chain of submodules here. I think we are not correct, because we have to take submodules here, right? I mean, if it were ideals, then that would be different, but the submodule generated by x1 doesn't contain the submodule generated by x1 square, isn't it? So only 9% left. Yeah, this is not correct. This is not correct. The submodule generated by x1 doesn't contain submodule generated by x1 square, because the scalars that you have here are precisely elements of z, right? Yeah, let me check the question whether it was for as Z modules or something else, because these are also rings, right? If we wanted to see whether this is an Artinian ring or not, we could use this argument, but for Z modules this is not the correct argument. Did you understand what I am saying?
No, sir, I'm not getting it.
Oh, so what I am saying is,
Yes, that was fine.
yeah, but this doesn't. What does a submodule joined by x1 have? I mean, what are the elements? These are elements of the form n times x1, right?
Yeah.
Where n is an integer. Now that clearly doesn't contain this, right? Yeah, that is what I am saying. So we can't use this argument here because we need to see whether this thing satisfies DCC as a Z module. That is, whether it satisfies DCC on its submodules, not on its ideals. So let me check the question once again. Which of the following Z modules satisfy DCC? Okay. Okay, and very surprisingly, the solution that they have given a solution here, and that uses this argument, but that's not correct, right? This is not a chain of descending chain of submodules, Z submodules. Okay, so maybe I'll just take some time, and maybe I'll stop the session here. I'll just fix it up and upload the write-up. Okay, and please do think about the Q mod Z one as well. And do you have any questions in as such, other than this particular one? Okay, okay. So maybe we'll stop now. Thank you for joining, and see you next week. Next week will be the final one. So yeah. Okay. Bye.